Record real quick. No Eliezer, no Tioni, and that's it. Everyone else is here. Okay. I didn't come back and change this after I finished making the lecture. I realized I didn't talk about the rings. So it's going to be asteroids and then some comparative planetology and not rings. So starting off, we've looked at this picture of the asteroids and the asteroid belt. We saw that the asteroids largely come in this region. That was black on black, which is the best way to be visible. In this region here between the Earth and Mars. Excuse me, Mars and Jupiter. Wow, that was bad. Like at the very end of the lecture, I'll show another graph that shows the distribution. And we can draw some conclusions from that. Actually, not near the end of the lecture. Near the end of the asteroids portion of the lecture. And we've talked about the numbers and the mass and whatnot. But now I'm going to talk a little bit more about some interesting things. Now, this is just a one-off slide. Well, one-off and then a clicker question based on it. This is Bode's rule. Bode, some person, noticed a pattern in the distances of the planets from the sun. Specifically, if you look over here, you can see the rule. The rule is n plus 4 divided by 10 astronomical units. That's how they use it, right? Yeah. And, excuse me?
Came right in the math.
Right in the math, yes. And so using this equation that he came up with, you can see that if you have n equals 0, that predicts 0.4 astronomical units, which is almost exactly where Mercury is. And if n equals 1, it's 3n. So if n is equal to 1, then you have 0.7, which is almost exactly where Venus is. And if n is equal to 2, it's almost exactly 1 where Earth is. Well, it's exactly 1 where Earth is. N equals, going on up, the next one, Mars, 1.6, 1.52. I'm good with that. Move on out, you have Ceres. Now, Ceres is a dwarf planet, but it's a big object, one we're going to look at a little bit more today. That comes almost exactly on. The next one, Jupiter, right on. The next one, Saturn, pretty close. The next one, Uranus, pretty close. Now, Uranus wasn't even known when he came up with this.
Oh, yeah, that's right.
So it's like, wow, it predicted it. Excellent.
And given the figures that he already had, that was still pretty spot on.
Yeah. Now you go to the next one, almost matches Pluto. So Neptune doesn't fit the pattern, but Pluto would continue the pattern. But then, of course, Eris is a little further off for the next one. You can see the pattern starts to break down. This is the situation that you come up with science. Remember the whole scientific method. Step 1, observe something interesting. Step 2, come up with a hypothesis that explains why it occurs based on scientific ideas that can be tested. Is this a scientific hypothesis?
Yeah.
No. It's not based on scientific ideas.
Based on that.
He saw a pattern. Seeing a pattern by itself is not a scientific idea. That doesn't mean that it's a wrong pattern. It doesn't mean that it's a foolhardy thing to explore. And I mean, this looked like a really good pattern, especially when you find Uranus and hey, look, see, I told you so. But it seems to have fallen off after that. There might be something to this pattern. There might be a scientific reason that explains something about these. When we talk about the moons of Jupiter, which will be after the exam because Wednesday we're going to have student presentation and then Friday the exam. Yes?
Doesn't Pluto have a two-orbital, orbit?
A what orbit?
Elliptical orbit.
Yes, it does. So this is semi-major axis
Okay.
for the true distance because yeah, it goes into that.
So that could make it back the way
Question, Ken.
Yeah, I have an unrelated question, but since the test is on Friday, does that mean there's homework this week? Or
Yeah, there's homework on Wednesday.
it's just it's the week after the test.
Yeah, because we'll have a student presentation on Wednesday, and then we'll have tests on Friday, and it would be homework over one day.
Okay.
I don't have it that way in the schedule, but when we got to practice, I haven't had one after the test for that reason. While we're talking about the test, I should point out the test will only cover material through the end of today's lecture. Okay, so what was that?
So boats and rule will still be on there?
Sure, it could still be on there, but we won't have things about the rings or the moons. That is about the moons of Jupiter primarily, Jupiter and Saturn. Okay, so there's Bode's rule. It shows intelligence, and it gives you something to think about and try to find a scientific explanation for. Question 7.
What does the N stand for
N
then?
is an integer.
Oh, so it's just 1, 2, 3, 4.
So it's serious.
Yes. 0, 1, 2, 3, 4. 0 for Mercury is for the 0, 1. All right. Now let's have a clicker question about this. How was Bode's rule developed?
Yes. The temptation is too high.
I'm glad you guys find the humor because not one person has laughed about where are the ice giants. I thought that was funny. I mean, you've seen the whole, Obama said he'd do this. Thor said he would destroy the ice giants. Where are the ice giants? Vote for Thor? Nobody was following my thinking on that question. Obviously, it had a legitimate answer as
When
well.
was this?
The pre-class for Friday. The last question was, where are the ice giants?
Oh.
See, when you said ice giants, in my head, I thought just the planets.
Yes, because that was the legitimate interpretation.
Should I?
You should go ahead and answer. Not that one.
You said answer.
Eliezer says this one. 3 people said that and 8 people that. Okay, turn to your neighbor. If it's Eliezer, tell him why he's wrong. Otherwise, discuss what you answered and what you think it should be.
He discovered it when he was going down the ice chart.
Okay, why
Well, yeah, I don't believe.
They were talking to each other. Tell them what the right answer is.
No, I was thinking of
Discuss.
Okay. So,
I don't think that's related at all to Bode's
there wasn't any experiment done. It was just, I see that there's a red bulb.
Is it B? It's B, isn't it?
I am going to re-poll it now, and we'll see how many people get the right answer. And please try to get the right answer.
Is it C?
I'm not telling you yet. I will tell you after. Yes, you're answering again.
Oh, answering again?
Yes, answer again.
And I can't not answer.
yeah.
Everyone but Eliezer is correct. And he's correct too. Okay, so the second time around we had all 12 people. A pattern discovered in the existing planets. It's not a theoretical prediction of Kepler's law. If it was a prediction of Kepler's law, then it would have gone as a scientific. But it wasn't based on scientific ideas, it was a pattern that was found. Now, remember when we talked about the emission spectra from light, and I had the lamp out here with the very specific lines? Balmer had an equation that gave the exact wavelengths for those lines that was like Bode's law. It wasn't based on scientific ideas, it was a pattern that he found. But then further exploration, and Planck was able to explain why Balmer's equation was correct. Okay, moving on. So, we're going to talk about some asteroids here, and I put in here a picture that was in the last version of your textbook. It's not in this version of the textbook, but this illustrates how knowledge changes and why I have to change textbooks in astronomy. I can't stay with the same version. That picture there shows a very fuzzy Ceres, a reasonably fuzzy Vesta. It's actually very clear Eros, but because Eros is so small, you can't tell that that one's really clear. Our knowledge about asteroids has been growing very rapidly. We didn't have much in the past. So it's only been recently, like in 2001, that Near Shoemaker landed on Eros. They actually crashed into Eros and it survived. They were pretty much out of fuel, and they said, well, for its last thing, let's crash it into it, see what happens. It crashed and survived, so then they took off and crashed it again because it survived the first time. And, there are things you can discover by that. You kick up any dust that's on the surface and you can analyze, so that there is value to it. It wasn't just like, hey guys, we got nothing better to do this week. Ceres is the largest of the asteroids. As we'll see on the next slide, Ceres is 1/3 of the mass of all of the asteroids.
Wow.
Which tells you how little there is besides Ceres. And in fact, if you go from Ceres to Vesta, this is 1/3, 33%. Vesta is 9%. So you have 42% of the mass of the entire asteroid belt between just these two. So there's not that much out there. It's just a bunch of little pieces for the most part. They come in very different shapes, sizes, and so we're just going to look at a few of them to get an idea for this. So first, Ceres. Ceres is currently being explored. In March of this year, March 15, 16, something like that, the Dawn spacecraft came into orbit around Ceres. And so since then, it has been studying Ceres. So before this year, we had no good pictures like this of Ceres. Just like Pluto, we now know what Pluto looks like. Now we know what Ceres looks like. Before, not so much. If you look at Ceres, you see some interesting features, and I have slides coming up with more of those interesting features. But right now, let's focus on, the diameter. It said 930 on the previous slide. 945, you know what? I didn't update the previous slide, but this one here is updated. Wrong conclusion. Our knowledge is improving. It's not growing.
What if it is? No. What if it is? What if it's like hitting other? No, you're right.
There's some evidence from the Dawn spacecraft that it might have a very ephemeral atmosphere, which would be pretty surprising. If you're going to have an atmosphere, you have to have an escape velocity that is faster than the velocity of the atoms flying around the atmosphere. And for that to occur for a small body, the atoms have to be going really, really slow, which means the temperature has to be really low. But there is some evidence that there's a little bit of atmosphere. Its density is, I hope I got this right, I did it by memory, 2.16 grams per centimeter cubed. Who remembers the densities of things like the Earth, Mars, Mercury? Well, for Earth is about 5.5 grams per centimeter cubed.
Pretty good.
Of those 4 inner planets, the lowest one is Mars. That's about 3.5 grams per centimeter cubed. It might be 3.3, but somewhere in that ballpark. So this is a lower density than the terrestrial planets. But then let's compare it to the gas giants. What kind of densities did they have? They were like 1.7 and lower, right?
1.3 for Jupiter.
So the gas giants were like 1.7 down to 0.7, if I remember right, grams per centimeter cubed. So they're focused somewhere around, 1.3 for Jupiter, like you said. So this is somewhere between. It tells us something to know that the density is somewhere between the densities of the rocky things and the densities of the gassy things. And what that tells us is it must be a mixture of the higher density rock and the lower density gas to get a density somewhere in between. Now, of course, I say the lower density gas, it's the liquid phase we believe we have here. We believe that Ceres must have a water layer. So now I'll zoom in so you can see a little bit better here. A rocky inner core, but then a water ice layer with a thin crust. Now, we are still learning quite a bit about Ceres because it's being explored right now. So we might learn more and have a different idea of what's going on in coming months and years. Because that Dawn spacecraft is going to stay there at Ceres until it dies. Here's probably the coolest feature that you've heard about on Ceres. Certainly the coolest I've heard about. These bright spots.
Ceres pyramid?
Yes, that also. The bright spots more than the pyramid to me. Those bright spots are real. They're legit. And what causes them? When the Dawn spacecraft was coming closer, they were taking pictures and they saw this bright spot. They saw a singular one. They're like, what in the world could that be? Is it a big mirror? Sign of humans? Got closer, get better resolution. Clearly you can see that that's patches of stuff. Now, what is that stuff? That's one option. One option is it could be some kind of ice. Staying in that vein, what do you think the other option would be? Not water. That was a good staying in the vein. The other idea is it looks kind of like salts would. Salts would also be very reflective. So we still don't know what it is. I remember this is really new. But not sugar. Although, I don't know if this was a joke or not. I haven't looked into it. But the story is that Comet Lovejoy has sugars and alcohol that it is giving off. And, yeah. That would be very interesting to people who believe in evolution because those are organic things. Those are things that are produced by living organisms. Not necessarily have to be living, but they...
Is Ceres between Mars and Jupiter?
Yes, Ceres is...
That's what I'm doing.
Okay, now the pyramid. This is what gets, the molders, Agent Mulder, excited. You see that pyramid and you say, on Earth we have pyramids. Almost every civilization has built pyramids. A couple years ago, went down to Belize and hiked up a pyramid. Very cool. In Egypt they have pyramids. There's pyramids all over the world. If you watch Stargate, the original movie, well,
Watched it.
what were pyramids?
They were interstellar gates. No? They weren't beacons?
No,
They were tombs?
they were landing pads.
Oh, that's right. That's dumb. I
Yeah,
remember now.
Spaceship.
I remember now. The spaceship
the
came down.
spaceship comes down and lands on it, yeah. And so, that was, of course, just fiction. Or was it? Raw. Anyway, moving on. So that gets people really excited. Maybe the same aliens that created all of the different pyramids on Earth made one on Ceres.
Or maybe we figured out the most effective way of making a structure so it wouldn't fall to pieces.
Okay, next, Vesta. Vesta is the second most massive and the second largest asteroid. The next one closest to it is very close in size but much lower mass. You had a question, ma'am?
Comment to ask that it is actually supposed to be spewing out 500 wine bottles of alcohol every minute.
The amount of alcohol contained Okay, so Vesta here. I'm going to change over to the PowerPoint presentation because the PowerPoint presentation has an animation here that, of course, I can't do with my PDF. So assuming that it comes up, there we go. So here we see Vesta in all of its glory. And here it's rotating. Now as it's rotating, notice you have these furrows or striations on it. Those are bigger than the Grand Canyon. Now this is a small thing, right? Only 525 kilometers in diameter. But those things are really big gashes. I'm talking about length.
Oh, they spin very fast. I can see that.
I don't recall its rotational rate, so I can't answer that.
Really massive.
Its mass here is 2.6 times 10 to the 20th kilograms. Compare that to the Earth. What's the Earth's? 5.9 times 10 to the 24 kilograms. So we are somewhere in the ballpark of 10,000 times more massive than Vesta.
Did you saw that?
So when you look at those scrapes, those troughs, what makes you think, or what would you think caused them?
I would think that scrapes.
Yeah, especially because I made a mistake and said that word.
Well, I thought about that before you said it. It looks like it might have hit something, or as it was going through its orbit.
Okay, and that is the theory. The theory is that those are scrapes left from an impact. It has a lot of impact craters. You can see, for instance, these craters right here, these three. These are called the snowman because it looks like a snowman feature. And
Give it up for
I didn't name it. These are impact craters, and they go in age along the order of size as well. So, it's almost like when you make a snowman, you make... Okay, I'll change over and fill it in for you. Don't want anyone to miss the snowman. So the snowman, here's the base, then here's the middle, and there's the head.
Has every one of those craters been named?
Probably everyone that you can actually pick out in this picture has been named. Because people study these different things and you want to have a name for it because it makes it easier to refer to it. Instead of X2357/29, /28 looks so similar. So they give them names. So now these are impact craters, but there are two very large craters that cover almost the entire thing. And it's believed that these striations are scratches that are left over from that impact. So that's Vesta. So we've looked at Ceres. Ceres, by the way, going back a slide. Got to go back 2 slides, it turns out. Okay, Ceres is a dwarf planet. What does it take to be a dwarf planet?
You have to
There's a rotation.
Okay, a lot of people said answers at the same time, which is good. It means a lot of people were thinking. And since a lot of people answered at the same time, I'll just go ahead and answer because I'm assuming I had all the correct answers between the two. Correct answer number 1. It has to have enough mass that gravity has formed it into a sphere. Does that have enough mass for gravity to have formed it into a sphere?
Yes.
Yes. Now, to become a planet, step 2, it has to dominate its region. Now, it's 1/3 of the asteroidal mass. It's not dominating its region. It's the biggest one, but it's not dominating it. So it can't be a planet, but the dwarf planets say, hey, it's reached one of the 2 goals, and they give it. Now, if you look at the next biggest one here, Vesta, whoops, once again, got to go 2. Vesta, which is still spinning on my screen. If you look at Vesta here, has that pulled itself into a spherical shape?
Kind of. It's like a potato sphere.
Okay, like a potato sphere. Almost. Well, speaking of potato spheres, here's Eros. That looks like a potato, right? It looks like a spud. Question. Like a bone? Bow. Yeah. This is theorized to be two objects that actually collided and stuck together.
Seems legit.
Now, something I haven't pointed out, I didn't put any, this is the last of my pictures of asteroids, didn't put any of this that have this. Asteroids can have moons.
You know, satellites.
Yes, satellites. We call satellites moons, if they're natural satellites. So you have like Dactyl, Ida and Dactyl, an asteroid with another asteroid that slowly orbits it. So when you look at the dynamics of these asteroids, it's not that different from us. It's still gravity that's controlling things. Things have to be a lot slower for it to stay locked in place and not lose things. I noticed it like 5 minutes ago, but I've been fighting and fighting to not laugh. So, I know, I failed eventually. Nobody's a perfect rock. How did asteroids come about? The theory of the asteroids, first of all, remember the mass. The mass is really small for the entire asteroid belt, much less than the mass of any planet. So the theory is that the asteroids in general were a protoplanet that was building up. It differentiated. Remember, differentiation is when you have the more dense things sink to the center, and then it got hit by something and broken into pieces. All the asteroids except for Ceres. I'm pretty sure they believe Ceres might be a remaining protoplanet. That it's still a pristine protoplanet that didn't get torn up, and that's existing in the asteroid belt with the other asteroids that are remnants of one that did get torn up.
Because it's so round.
I can't give you all the reasons because I'm not aware of them. Sorry. So when you look at the asteroids, we have different kinds of asteroids. If asteroids came from this part, they might have never gotten very hot. And so you could still have things like volatile gases locked into the rock because they didn't get baked. Things that came from lower in, like here, would have been very hot, and that drives the gases out. So you don't have what we call the volatiles. You don't have the gases that would be there. And then, of course, this part here, that would be metallic rather than rocky. So asteroids should come in those varieties. Most of our study of what asteroids are like comes from things that have hit the ground. Right? It hits the ground, we call it, when it's in the sky, you have a meteor, which is light. When it hits the ground, you have a meteorite, which is the rock that made it to the ground. When you study those meteorites, even though most meteors are little tiny things, the grains of sand, anything that makes it to the Earth is going to be bigger. It's going to be probably part of an asteroid. And so then you can check. And some of the asteroid or some of the meteorites are iron. Like if you've been to the Barringer meteor crater, I don't think I told you this. They have a big chunk of iron. And when I went there the first time, our tour guide said, and if you can pick it up, you can keep it. And I was able to make it move. He got really, really nervous. I wasn't able to pick it up though. I think it's like 500 some pounds. It's not like you just go, yeah, sure. It's made out of iron. In fact, Barringer purchased the meteor crater site because he theorized that the meteorite, would be like a huge iron object, and he could mine the iron. That's why he purchased the site, to mine the iron from the meteorite. But the biggest piece they found was that one piece. Other meteorites are clearly rocky. Some have these things called chondrules, which are little glassy rocks, variations that would come from being different parts of that structure. My last picture on asteroids, showing where asteroids are found in the solar system. And what you find is there are certain places where the asteroids are specifically not found. And those places correspond to resonances in the periods. Remember from Kepler's third law, we know that the period of rotation depends on the semi-major axis. And so these places that I've marked with my red lines that are shown with numbers above are the ratios of the periods of orbit between Jupiter and something that was orbiting in that location. So there's clearly something that is saying we can't have asteroids hanging out in these small integer ratios to the period of Jupiter. And the reason for that, I'm not going to ask you to reason it through. I'll tell you the reason through. The reason is every time Jupiter comes around, it's going to pull it toward Jupiter. And so it's like you're in a swing. If you're in a swing and there's somebody pushing you, if every time you come back they push you, you're going to move bigger and bigger and bigger. If, on the other hand, they're just pushing you at random times, nothing's going to happen. You're just going to stay barely moving. So it depends on when you push how the motion's going to work. And so, of course, with the swing, if you pushed every time they came back, they would get bigger and bigger. If you pushed every other time they came back, it would also get bigger and bigger. Or if you pushed every third time, right, you can see how those resonances would make it bigger if you're pushing a multiple of the period of the object. And so that explains the 2 to 1, the 4 to 1, the 3 to 1. Now the 5 to 2 is a little more complicated, but it's the same idea. You're working with a resonance. And what happens is, just like in the swing, a planet or an asteroid that was in that region would get yanked to a larger orbit and then go back down, and it would probably collide with things and fall into a new orbit. And so it's the moving up and down instead of staying in a circular orbit that makes them hit things and then fall into different orbits. So that's what clears them out. When we get to talking about the belts, or the rings around planets, the same thing occurs. You have regions that are cleared out in the rings because of resonances like that. Okay, so now looking at the specific comparative planetology chapter. We have pictures here looking at the surfaces of the rocky planets as well as the moon. The moon is obviously not a planet, but it's interesting to look at it as well. And when you look at these, you see things like, what's the primary feature in this? What's the primary thing you see there? Don't worry about the color. Craters. Right? We look at the craters. If we look at the surface of the moon, they don't have any pictures that show crater. Well, there's this one here that shows craters similar. And here is a crater on Mars. Craters on Venus. We see craters in all these pictures except for the one on Earth, and we know that there are some craters on Earth. Not nearly as many, though. Why not as many on Earth?
Because of erosion and
Erosion and weathering and erosion. The fact that all of our craters have pretty much been resurfaced by the action of the Earth. So we have craters everywhere. Do you remember what these things are?
pancakes.
They're pancakes. These, actually, yes, this is not a crater. I was wrong. That is Olympus Mons. It's a volcano. These are volcanoes, and this is a volcano. There are craters on Mars, but apparently there's no pictures of them. We have a lot of similarities, a lot of differences. On Earth, we're the only one that has liquid water. That makes a big difference. In fact, I have a whole slide on liquid water, so let me not spend a lot of time on liquid water on this, and instead just move on. If you have a smaller planet, it cools quickly. Remember the example of having food on a fork versus food in the pan. It'll take a long time to cool in the pan. It'll cool very quickly on the fork. So you expect the bigger ones, like Earth, to not have cooled nearly as much as the smaller ones, like Mercury. I am going to just go forward from there. This here is another graphic of the stages of planet formation. We had planetesimals coming together, getting larger. You form a solid crust. You have lots of cratering. You have differentiation. Differentiation would have to occur somewhere around here because it doesn't have it listed. Differentiation, lots of cratering. You have the flooding. So this combines cratering and flooding there in the same one. Then you have tectonic action. When you have a molten core, that molten core is going to drive convection currents of molten material that's going to cause plate action, the motion of the surface plates. The Earth still has very considerable tectonic motion. Hence we have earthquakes and whatnot. Over time, though, as it cools, you'll have a freezing of the core. You'll stop that tectonic action. And so Mars, a smaller planet, has pretty much solidified the core and stopped its tectonic action. Mars. Mercury, smaller one, further stopped. And of course, the moon, even smaller, its interior is just plain old frozen. So why is moon frozen, whereas Earth is not?
Far away from the sun.
Well, the Earth and the moon are about the same distance from the sun. Okay, greenhouse effect. Greenhouse effect will affect the surface temperature, but not the temperature in the core. Now, not very much. You do have the cooling rate. Primarily, it's because the moon is small and the Earth is large. Because the Earth is large, it's going to take a lot longer for us to cool down. Moon cooled down quickly. All right, here's the slide that talks about water. Water is extremely important to us. We look for it everywhere we go. As you know, they believe they found signs of seasonal water on Mars. The water on Earth has acted to remove carbon dioxide from the atmosphere, giving us a smaller greenhouse effect, making it so the temperatures are not as warm as they would have been. If we had too much CO2, runaway greenhouse effect. If we had too little CO2 and too little water vapor and too little methane vapor, then we would have too cool of a surface, would be more like Mars. And, CO2, what makes CO2? Burning things. Or we also have, when we breathe out CO2, right? So when we breathe, we also produce CO2. We're bad. We should just get rid of humans. No, we shouldn't.
Introducing the new Tesla electrical human.
Yeah. Okay, sunlight. Sunlight is obviously super important for life on planets. If we didn't have sunlight, we would be frozen. Just like if we didn't have the greenhouse effect, we'd be frozen. We need sunlight to catalyze things. Venus, being closer to the sun than the Earth, receives more sunlight than us. With its heavy atmosphere, it retains more heat, hence it's super hot. Mercury's even closer to Venus. It's going to get more sunlight per unit area than any of the other planets. But it doesn't have atmosphere to lock it in, so the side that's in shadow can get very cold on Venus, whereas the side that's in sunlight gets very hot. Or not Venus, I meant to say Mercury. You go out to Mars, farther away, right, it's 50% farther away from us, and so it receives significantly less sunlight than us, so its highest temperature is only 68 or so Fahrenheit. 70 Fahrenheit, let's say that among friends. You go out even further to where the gas giants are, it's really stinking cold because they're far from the sun. The frost line is a very important piece to the hypothesis about planet formation. The frost line is the region where the temperatures during the formation of the solar system were low enough that you can have molecules stick together, condense. And so where you can have molecules stick together and condense, then you can have planetesimals hold on to the volatile gases. So plants that form beyond the frost line could hold on to all kinds of gases and grow very large. Ones that form closer than the frost line, closer to the sun, it was too hot, they couldn't have water molecules stick together. They couldn't hold on to water, and so there was virtually no water that they held on to. You have the same mix of chemicals, but they just can't hold on to them, so there's a lot less that they can keep. Didn't grow nearly as big. So all of these pictured here, except for Earth, right, here's Earth for comparison only. Everything else in this picture are plants that form beyond the frost line. You can see they're far bigger than Earth. And each one has a rock that's comparable or larger than this rock in the Earth. But then they just have all the gases around them. How many of these have rings, not counting Earth? All of them have rings. You can't see the rings in these pictures except for Saturn, but all of them have rings. It's just Saturn's is the only one that's thick enough for us to see from Earth. Nice mustache. I know, you've been growing it for years. Okay, our next question. What is the distance where temperatures were cool enough for water to freeze during planet formation? Thank you for changing, Lauren Lee. Although I can't be sure which one you changed to, because at the same time you changed away, somebody answered an incorrect one. Okay. The frost line was the correct answer. The asteroid belt, where's the asteroid belt fall? Between Mars and Jupiter. The frost line is also between Mars and Jupiter. But just because they fall the same place doesn't mean that they're both the right answers. The frost line is the specific name for that location. Where's the Kuiper belt? Yeah. The Kuiper belt is beyond, well, Pluto is actually part of the Kuiper belt, but it's beyond Neptune. I know Pluto technically crossed inside Neptune. The Oort cloud is even farther out. The comet line, that one doesn't exist. The separatrix, in terms of astronomy, it doesn't exist, is a mathematical term. So anyway, all but two people got it right. Looking at equatorial bulges. I tend to have an equatorial bulge. I bulge right here, right? I tend to. Now, the planets are rotating. And because they're rotating, you spin around a circle, your hands naturally come out, right? Well, that's what's going on with the planets. They're spinning around a circle, and the equator is the place where, if you have a sphere, the equator is the farthest from that axis of rotation, and so it's got the fastest speed, it's got the most getting out there. And so it causes equatorial bulge. So if you compare something like the Earth, the figure on the left, you see that the Earth's equatorial bulge is about 22 kilometers. (21). And of course, if you take 21 and divide it by the Earth's radius, that's a very small percentage bulge. Now, if you look at Jupiter, you have 4,637 kilometers difference in the radius at the equator compared to at the pole. And if you take the fraction of 4,637 to, let's say, 71,000, that's a much bigger fraction. We would say then that Jupiter is more oblate than the Earth is. Oblate is the three-dimensional equivalent to eccentric. So we talked about ellipses being eccentric. If the eccentricity was 0, it was a circle. But the bigger the eccentricity got, the more non-circular it became. Oblateness is exactly the same idea. If the oblateness is 0, it's a sphere. But the bigger the oblateness gets, the more elongated it gets. Hence that term that a football is an oblate spheroid, blah, 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 blah. You probably heard that speech.
So foot oblate.
Not even going to talk about that. Here is something, well, no, that's not here. I thought that was talking about differential rotation, which is totally cool. The rate at which the equator of Jupiter rotates is not the same as the rate at which the pole of Jupiter rotates. You can't have that with a solid sphere. For the Earth, everything rotates at the same rate. But on Jupiter, the poles rotate faster and the equator rotates more slowly. We call that a differential rotation. The Sun is just the opposite. The Sun rotates the fastest at the equator and the slowest at the poles. Okay, differences in our planets, our gas giants. Every single one of them has rings. Saturns are easy to see. The rest of them, not so much. They generate heat internally from Friday. You should be able to tell me, how are they generating that heat?
Flip Friday?
Yes. Yes, I do.
Is there a Flip Friday this week?
No, from last week.
Oh, okay.
How are they generating that heat?
From pressure.
From things falling in.
Yeah.
Like droplets of liquid helium falling in. And the gas giants are all generating more internal heat than they receive from the sun. And they have many, many moons. Come on, click the question. Nope, not yet. The color differences. What makes the colors of Neptune and Uranus? Methane gas. Why are the colors different?
Based on the light.
One has more methane than the other. The methane absorbs red. So having a little more methane in the atmosphere absorbs a little more red, makes it a little bluer. Now, the color differences between Jupiter and Saturn and Uranus and Neptune have to do with temperature. As the temperature gets cooler, you're going to have different phases of your materials, ice, liquid, and that is primarily what makes the differences. All of these are largely hydrogen and helium in their atmosphere. In fact, clicker question that you're not going to see is, this is the last thing we'll do. Clicker question you're not going to see is, what is the approximate percentage of hydrogen and helium in the atmosphere of both Jupiter and Saturn? The answer is 100%. One's like 96% and 4%, and 90% and 10%, both basically 100%. Okay, which statement is untrue about gas giants? Okay, we had 10, 1, and 2. The correct answer was this one. They do not have liquid surfaces. If you were to fall into something like Jupiter, you would never splash. It would just get thicker and thicker and thicker and thicker and thicker.
Until you're crushed.
Well, yes, but... Okay, have a great day.